In this video, we're gonna go over the intermediate value theorem, which says that basically, if the function gets from one point on the y um, to another point, then it has to actually take on every single point in between. So, for example, here's our graph x and y axes, and let's say we have a line that goes up like this, and let's say that this value is 2 and this value is 4, and we know that. So this is going to be a on x and b on x. So we know that at when x is a, the y value is 2. When x is b, the y value is 4. Then we know that somewhere within this interval, the function took on every value between 2 and 4. So at one point, it had a value of 3, or 3.5, or 2.01. So it had to go through all of these values in order to go from 2 to 4. And like it says, while the theorem is intuitive, the proof is actually quite complicated and requires higher mathematics. So we're not going to go into there. We're just going to take it as is. And one of the takeaways from this theorem that is going to be helpful to us is that if we know that the function was negative for some x value of at a, let's say x is a, y is negative, and then we check it again at a different x value, we'll call it b, and it's all of a sudden positive, that we know that the function had to cross the x-axis somewhere in between a and b. Okay, so it's basically like if I was spotted on the US territory one day, and then I was spotted in Mexico the next day, they know that I had to cross this borderline somewhere in between yesterday and today. So basically that's that's what it is. And actually, why are we concerned with that? Again, it's the issue of finding your zeros for polynomials of higher order. It's a whole new task that we haven't encountered before. When we have a higher order polynomial, we don't always have tools to spot zeros. So we should employ everything that we can in order to spot those zeros. All right, so using the intermediate value theorem, here we have a function f of x equals x cubed minus 5x squared plus 3x plus 6. And we're asked to prove that it has at least 2 real zeros between x equals 1 and x equals 4. Okay, so first of all, let's find the function values at 1 and at 4. So at 1 we have 1 cubed minus 5x squared plus 3x, 3 times 1. So we are substituting ones in for x's. So what do we have? We have 1 minus 5 plus 3 plus 6. That's 9. 10 minus 5 is going to give me positive 5. Okay, let's check the sign at 4x equals 4. So we have 4 cubed minus 5 times 4 squared plus 3 times 4 plus 6. I think I got my signs right. this time. And the function value there is 2. So positive and positive. Now we want to show that there is at least 2 real zeros between x equals 1 and 4. So basically we have a positive value at 1, and it's, I mean, my drawing is not up to scale, so and it's positive again. So in order for the function to have 2 real zeros, it has to do something like this between 2 values. So somewhere in between 1 and 4, it should have a negative function value. So let's check some values in between. We could check whole values first, like 2. I would do 2 and or 3. But then if those are positive as well, I would check the values in between, which could be a tedious process, but let's hope that we'll catch that negative value right away. So let's try 3. Let's say 3. F of 3 is 3 cubed minus 5 times 3 squared plus 3 times 3 plus 6. All right. And bingo, I got a value of -3. So basically right here for positive for x when x equals +3, the function value here is -3. So basically I have positive value for f equals 1 and the negative value for f equals 3. So that means that the function crosses the x-axis once between those two values. And also I have negative at f equals 3, at x equals 3, and the positive for x equals 4. So again, the change in sign means that the function crosses the x-axis there once again. So here's my statement. It says f of 1 is negative and f of 3 is f of 1 is positive and f of 3 is negative. Therefore, the 3 dots, the function has a real 0 between x equals 1 and x equals 3. Number 2, f of 3 is negative, while f of 4 is positive. Again, different signs. Therefore, the function has at least one more real 0 between x equals 3 and x equals 4. We can never be sure that it's only one because the function could actually cross the x-axis several times. So, but we know that there is at least one real 0 there. Now you can try it by yourself and try to prove that the following function has at least one real 0 between x equals 1 and x equals 2. And the function is 7x to the 5th power minus 9x to the 4th power minus x squared. And again, the x values are 1 and 2. So go ahead and pause here. And I will, this is it for this video. I'm gonna see you in the next one.